So we cover a full range of services, covering industry-wide recognized assessments and standards, from specifics such as immediate integrity to comprehensive studies, for example, a fitness for purpose. We understand the importance of leveraging high-resolution data, and for this, also NDT has created its unique approach for specific methodologies, for example, dense strain. So standard methodologies follow ASME B318 2018, considering only the deepest point of the deformation. Knowing that we have an ultrasonic geometry tool, we can also follow the same approach of B318, but considering a point-wise calculation of the longitudinal membrane, leveraging this high-resolution ultrasonic data. So we try to ensure that all the data is being used and all the data is being enhanced for this inputs assessments, not only providing the assessment as written. We also have support and consulting services when the operator has a unique or specific challenge. And in these cases, our integrity engineers can provide recommendations and solutions that are not necessarily covered by industry-wide recognized assessments. So I will guide you through some case studies ranging from the simplest enhancements of input data, sophisticated studies being conducted during the analysis of a run, and I will finish with some complex assessments. So the first case study is when we're dealing with standardized reporting. So we know that there are certain things as interaction rules covered by API 579. So if we understand this interaction rules, we know that, for example, in this case, both lengths of target anomalies are taken into consideration, then the average is calculated, and if the actual gap is less than the depth, the anomalies can be joined together. But what happens when operators have long threads or interesting morphologies? So we understand that there's relevant crack lengths, and we understand that there's also part of the crack that it's not necessarily deep. So what happens when we input this information to an assessment? Typically, we will receive something conservative. So us as analysts and us as NDT, we need to challenge this standard rules and try to ensure that the operator receives the best input possible for their IMP. So in this case, we took one anomaly, one feature to a laboratory, and we understood that this feature, if we use the common interaction rules, it will be sized as 15.5 inches. So if we do a standard assessment, in this case, modified log secant, we know that the original burst pressure calculated is 1500 PSIs. But what happens if we start thinking this in terms of what kind of amplitudes are we receiving, what kind of profile are we seeing, and how is this anomaly behaving in the data? So with this, we can understand that, yes, the anomaly is quite long, but just part of this anomaly has the highest amplitudes and the deepest profile. So if we consider only this side, we can narrow it down to 6.2 inches, and this input will change the crack assessment, giving us almost 1900 PSIs. So when this anomaly was taken to the lab and it was hydro tested, the real p-burst was, again, almost 1900 PSIs. So what happens with this? Providing just the standard interaction rule is giving an extremely conservative assessment to the operator and taking him immediately to the ditch. Let's say if they're operating a little bit above 1500 PSIs. For the second case study, we had even a longer anomaly. In this case, almost 35 inches. So again, the anomaly is 35 inches long if we use standard interaction rules. But what happens when we go back to the amplitudes and what happens when we go back to profiles and depths? Well, with this, we recognize that instead of having one anomaly, we have 5. And from those 5, 3 are the deepest points of the crack. So if we size those cracks individually, we get that the deepest one is 7.5 inches long times 98 mils deep. So calculating 34.5 inches times 98 mils will give us a p-burst of 1,476 psi's. If we just narrow it down to the deepest anomaly and longest anomaly of those 5, we have 1,723 psi's. Well, this joint failed at 1,882 psi's. So again, standardized reporting will, in some cases, provide conservative results, but if the IMP of the operator is understood, the challenges are understood. Also, mechanical properties, history of the pipeline, and other variables, all of this can be taken into consideration to tailor a specific analysis to provide better input data and at the end, ultimately providing better assessments. So as I mentioned before, for us, it's important to consult with the operator about its pipeline history, challenges, concerns, also to understand if there's a need for something very specific done from scratch from the beginning of the analysis. And this will eventually mitigate sifting through an abundance of information, going back, reanalysis, reissues, and basically doing what it should be done from the beginning. Then I'm going to talk about how we conduct run-over-run comparisons internally, and also when we take it to a crack or corrosion growth assessment. So for this, this is very important because from the beginning, there's already insights that could help the operator understand how certain features are behaving. So as standard procedure, if we have an inspection that was run historically, we will use all this information from the beginning to understand how the new information, how the new data is behaving, and to identify patterns, outliers, but this going into depth, not only comparing one value to the other, understanding how the robots work, understand how the amplitudes are being collected, and basically creating a lot of statistical studies to identify all of this. So in this case, the simplest approach when a run-over-run comparison is done is to compare depths. But what happens when you compare one depth to the other? There's a lot of uncertainties. The first uncertainty is what type of tolerances do the tools or robots have? What type of variables are missing? If there was a different temperature when this tool was run, different pressure, things that could affect the data. So in terms of comparing depths, we also do it. We create histograms to understand that the distribution is aligned to 0 or is the tendency is going through a positive or a negative. If we see the right side, this is a moving average chart where we can see the 0 line, then the red line that's a moving average, and then 2 dotted lines that tell us exactly what the statistical tolerance is. So we know that the robots have a specific tolerance, but what happens when we're compounding information? We have to take in consideration this statistical tolerance as well. So in this case, when we have something beyond that statistical tolerance, there is something being identified. In this particular chart, you will see that green anomalies are things that are already repaired, considered stable. And in this particular case, we have 2 that have significantly shown change. So what happens? In this particular case, in 2017, we performed an inspection with a high resolution robot, and after 2017, the pipeline was hydro tested, and then in 2018, we ran the same inspection robot again. So for this particular anomaly that we were seeing on the screen, this was repaired in 2017. But during the analysis, when we just comparing depths by its own, we noticed an increase of 70 mils from one year to the other. Then we went a little bit deeper to understand the profile. So in terms of shape, the profile is pretty much exactly the same, but in terms of depth, it's completely different. So we know that something odd is happening. And this is something that from the very beginning, the intention is to communicate it to the operator, because statistically it shouldn't be happening. And also in terms of data, it is an outlier. So talking about what else do we check on the data, all the other variables. Well, when we're talking about ultrasonic robots, we're talking about amplitudes that are then being translated into depths. So it is paramount for us to understand how these amplitudes are behaving. This is pretty much the foundation of what we will gonna report. So all the ultrasonic tools, depending on its resolutions, will show significant variance. This variance has been proven and tested in the lab. So us as NDT Global, we understand how different tools will behave if we're running them consistently. So if we run it twice or we run it 10 times, we know that there's going to be a variance between one inspection to the other. That's just a physical understanding of how tools work. So if we see the chart above, for this particular inspection, we understood that we were running a high resolution robot and that we were expecting a 3 decibel variance between one inspection to the other. So what we have to do is compare every single amplitude that we are receiving from one inspection to the other to ensure that the distribution is following this 3 decibel variance. And in this case, it was. And it was actually quite tight. So knowing this, we can ensure that everything is behaving as designed or engineered. And when we translated it to depths, we should see the exact same trend. So if we go to the right side to the Unity plot, we will see that we have 2018 on the y-axis and 2017 on the x-axis. In this case, the green lines delimit the tool tolerance as designed, 40 mils. And the blue lines delimit the statistical tolerance. So even not considering the statistical tolerance, everything is behaving as within 40 mils as expected and as designed. So this is extremely important. This is something that it's being done from the beginning for every inspection that we have. All these outliers, variances are communicated and explained to the operator beforehand, but we can also create comprehensive studies out of it. These comprehensive studies could be translated into a crack growth assessment, like the example we have on the screen. This is a very simple table, one page, where we explain all the information that we're getting statistically in terms of how many anomalies we are comparing, what type of anomalies we're comparing, if they're crack-likes, if they're manufacturing related, if they're SEC. But the key thing here is that knowing all this information, knowing that the tools are working as designed, we are confident that this statistical information is very relevant to operators. And in this case, we can see that after the hydro test, crack-likes are showing a statistical growth, not significant, but there is proof that there's statistical growth, and manufacturing indications are not showing statistical growth. So with this, it's also proven that, well, we have time-dependent features that are showing significant growth, and we have non-time dependent features or stable features that are pretty much remaining the same. Now I'm going to talk about something more complex, finite element analysis. So what is a finite element analysis? Well, it's considered as level 3 by API 579. It's considered probably the most comprehensive assessment to provide an accurate estimation of a failure pressure, stress level, or degree of deformation. And it's also one of the best approach when assessing complex anomalies and combined stresses. So what is the value received from an FEA? So we know from internal studies, external studies, and history that FEAs provide the best estimation of a failure pressure. So if we see the chart on the left, this was a case study that we had with a metal loss feature where we estimated the failure pressure using common methodologies such as B31G, modified B31G, effective area, the MBRPF 101, and at the end, a nonlinear FEM. And from all of those, the nonlinear FEA was the one that provided the closest burst threshold to the real tested one in the lab. Also, we know that FEAs are extremely good when we're assessing uncommon threats, like the ones that we had at the right, that we have a seam over trim defect. This is not necessarily understood. There is no common assessment to deal with it. So we can do an FEA on defects like this to understand the morphology, to understand the behavior, and to model how they will react on time. So what happens with input data? So input data is the most important aspect of an FEA. So before, we had input data from MFL tools, caliper tools, which we could provide a good FEA. But there's a lot of variables not being considered with this input data. There's liftoff of arms, there's sagging, there's additional things happening that will provide noise and will limit the quality of the model. So our idea from the beginning is always to design engineered technology that will provide the best data and also the best input data for things such as an FEA. So this is just an example. At the very bottom, we have our ultrasonic geometry. This is completely touchless. There's no mechanical arms. There's nothing touching the pipe body. It's pretty much an internal diameter scan of the feature. So this will ensure that the model is not coarse and that the model is the most precise possible. So I'm going to talk a little bit about how we analyze FEA data, because for us it's extremely important that the input data has the highest quality to ensure that the model and the assessment, whatever we're calculating, is the most precise possible. So we conduct our own analysis. So the same people that work with the FEA models understand the tools, the robots, the precisions, the variances, the amplitudes, and how this data is being translated into a result. We also understand how these tolerances could affect a model. And at the end, we have a very thorough process in terms of how we handle the data and not just creating a model assuming different variables. Because assumptions for models like this are the difference between something precise and the difference between something conservative. So starting with one technology. This is a crack simulation that we performed using one of our high resolution small diameter robots. So first we have the data. So if we go to the top left, we will see that this is the profile we collected from the tool. So this is something that the analyst can see, and this is something in general terms simple to extract from the data. So we have the understanding of this profile. So what happens when we take this profile and we create a model out of it? Well, we have to ensure that we're not using that we're using the exact or closest to real profile of the feature, because if not, we end up with something rectangular, something semi-elliptical, or something with a canoe shape. But the intention is to have the most precise profile possible. So we're able to model this crack profile with FEA, and in this case, we were able to compare it to a freeze break, just ensuring that our data and how we're handling it compares to something real. So this is for crack tools. Then we have the same case study for an ultrasonic geometry. So what we decided was to test our ultrasonic geometry tool against one of the best NDE methodologies available for deformations. This is laser scan. So we took our measurements with ultrasonic geometry, and almost immediately this anomaly was verified with laser scan. So what happens when we compare this information? So on the left side, we have the UG robot model, and on the right side, we have the laser scan model. So using all this information, we are able to calculate the outside diameter, the internal perimeter, internal diameter, external perimeter, and outside diameter. So from the very beginning, just checking this calculations, we know that they're pretty much exactly the same. So we have 15.49 inches as an example for outside diameter calculated by the UG tool, and 15.34 inches calculated by laser scan. When we take this to stress calculations, deformation results, this is when it gets interesting, and this is when we have to ensure that we are providing the best result possible. So on the left side, we have the UG robot model, and on the bottom side, UG robot model, and on the top side, the laser scan model. So in both cases, we are getting pretty similar results. Laser scan is giving us a stress result of 47,715 PSIs, and the UG robot is giving us 52,506. So there's a difference of 5,000 PSIs. This difference is almost not relevant. It's pretty precise for the type of comparison that we're doing. For the deformation results, we have the laser scan giving us 0.033 and the UG robot giving us 0.058. So again, we have a delta of 0.25 inches. This is pretty close to what the laser scan data is giving us. So what does this mean for us? We know that the UG tool is yielding results comparable to one of the most precise NDE methodologies. And we can not only use this UG tool to get a point-wise assessment, we can use this UG robot to create a full 3D model of a joint with the most precise shape of the joint possible, without the need of doing advanced or sophisticated NDE. So we know that crack data can be used to get precise profiles. We know that wall thickness data can be used to get precise measurements, direct measurements from wall thickness. And we also know that the UG robot is yielding amazing results when creating a shape of a joint. So what happens when we combine this information? Because most of the time we're running combined inspections. We run all of the tools, or we run two of them. So what happens when we combine all this information? Well, we also had to do a case study of integrating all this information into an assessment. So for this, I will pass it to my colleague Diego, that is in charge of this initiative, and he's been doing some amazing work in Latin America, combining all inspections.
Thank you, Santiago. This is a case study related to one finite element analysis that we performed for a customer in South America. We performed the full analysis of a joint that contained two external metal loss and one crack-like anomalies. This pipeline is used to transport gasoline for aircrafts in one airport. This is one strategic pipeline for the city and the country. So it's very important to ensure the mechanical integrity of this asset. It's a pipeline of 6 inches of diameter, built with API 5LX42 material specification and 9.3 millimeters of wall thickness. NDT Global performed their inspection using the ultrasonic geometrical robot, UG, the inspection of metal loss pitting using UMP robot, and the crack inspection using UC robot. After the runs, after the data analysis was finished, and as a result of fitness for purpose analysis, some anomalies were found as non-accepted to remain in service. It's important comment that this assessment was performed using methodologies level 1 and level 2, common and traditional methodologies. The problem was that these anomalies was located in the same joint, in middle of one high consequence area. The presence of one water body and two near villages generated a very complex scenario to repair immediately. The option proposed by NDT Global to customer was to use the FEA methodology to evaluate the entire joint, including the 3 anomalies. Of course, using the data collected by the inspection robots as source of information related to the geometric pipe and anomalies. In the integrity department, we started with the analysis, extracting the information from each technology. After we create the 3D geometric model of the pipeline using the internal diameter measures performed by UUG robot, we create one internal surface model. Then, using the wall thickness record collected by UMP robot, we incorporate in the model the real wall thickness of the pipe, and now we have a three-dimensional realistic model that considers the metal loss areas. And the last step in the modeling is include the crack-like anomaly. In this case, the profile was measured by UC robot. We use these values to create the geometric of the crack model inside the principal model. And finally, the integrity engineer defined the simulation conditions related to mechanical loads and material properties. And then we run the simulation and analyze the results. In the left side of the slide, you can see the resulting views of the simulation for the complete joint and the anomalies. The FEA results are displayed using scale colors. In this case, we only show the results corresponding with the stress levels. The results obtained in this analysis in terms of pressure failure, safe pressure, stress levels, and deformation degree indicated that the pipeline section that contains these anomalies is accepted to remain in service. But now the operator have one assessment with the highest level methodology that support their decisions about to repair or no repair or repair in other moment. Additionally, with the FEA, it's possible to assess the fatigue life of the pipeline subject to analysis. And this simulation software, we consider one operative pressure variation and one time value that define the load cycles. It's possible to use the operative records, of course, but in this case, the customer defined the operative cycles between 700 psi as minimum value and 1,400 psi as maximum value, with one time between one value and the other of 24 hours, 1 day. The model used by the simulation software to simulate the fatigue behavior was the Gerber model, and the results obtained indicated that the remaining fatigue life of the pipe is 4 years below these conditions. In the right side of the slide, you can see the resulting views corresponding to fatigue life assessment, defined in the joint by the crack-like anomaly. This is an excellent example of FEA where we use the currently capabilities of ultrasonic robots to perform the best possible integrity analysis and solve special problems or necessities